In the pre-program work for this program, we gave you a table of data. This data was obtained from an experiment like this one. Different masses were suspended from an elastic band, and the resulting length of the band was measured. When you plotted the data points, you should have found that they lay nearly on a straight line. We asked you to draw the straight line that you thought best fitted the data points and to find its equation. You were then able to make predictions about how long the elastic band would be if you hung some different weights on it, without actually doing the experiment. And of course, this is a process which has lots of applications, because we can use the data from an experiment to make a reasonable model, and in this case, it's a straight line, and then use the model to make predictions. Norman.
I had a go at fitting a line to the data that you had, and this is in fact the line that I drew. As you'll have found, it's not possible to get the line to go through all of the points, but this seemed to me to be a pretty good fit. Now, let's look at this line a moment. What does it tell us? Look at this point where it cuts the axis. This corresponds to no mass attached, and so this will tell us the unstretched length of the elastic band. I drew it actually a bit more accurately, and my one came out to be 205 millimeters for this distance. There's something else I can predict as well. Suppose I had this mass on the elastic band. What would happen if I added another 1 gram to the mass? How much further would the band extend? Now, you may remember that that's one of the questions that we asked you before the program. Well, if I increase x by 1 and then try to measure the increase in y, I get such a tiny triangle here that I won't be able to measure anything. But what I'm actually doing is measuring the slope of the line. And to do that, I can use any convenient increase in x. So let's use 100. If x increases by 100, then y increases by this amount. I worked that one out as well, so I'll just look at my work I did before the program. That turns out to be 14. So for a 1 gram increase in the mass, the length would increase by 1/100th of this value. That's 0.14 millimeters. Now, the next thing we asked you to do was to write down the equation of the line that you had drawn. Can I do that for my line? Well, what's the general form of the equation of a line? It's this: y equals mx plus d. And remember that m is the slope. And we've just found that that was 0.14. So m is 0.14. Now what about d? Well, d is the value of y when x is 0. And we noted earlier that for this line, that was 205. So d is 205. So the equation of the line is y equals 0.14x plus 205. And that's the equation of the line that I've drawn. Well, I hope you managed to do those problems before the program, but if you did, I bet you didn't get exactly the same answers that I did. You see, when I drew this line, I had to use some judgment about what I thought was the best. But you may well have drawn a different line, and it would be difficult to agree which one was the better.
Well, this is a really rather unsatisfactory state of affairs, isn't it? If this process of fitting a line is to be of any use at all, we must be able to agree on one particular line. And to do that, we need a criterion for deciding which is going to be the best fitting straight line. Well, the criterion we choose depends on what we're going to use the line for. We want to use the line to predict the value of y, that's the length of the elastic, for a given value of x, that's the suspended mass. Now, our data points don't actually lie on the line, so whichever line I choose to fit the data, some of the data points won't lie on it. And if I use the line to predict the value of y at one of these points, there'll be a difference between the predicted and the measured value. In other words, there are bound to be errors in our predictions. Well, in looking for a criterion for the best fitting line, we'll have to take into account the errors at all the data points. How do we compute these errors? Well, let's consider the line y equals mx plus d, and think about the error at the first data point. It's this distance. Well, x is 100, so the predicted value of y is m times 100 plus d. On the other hand, the measured value of y there was 228. And so the error is 228 minus m times 100 plus d. In other words, it's the data minus the fit. It's the residual. Well, if I take a general data point, xi, yi, the error, or the residual, that's ei, is going to be the measured value, that's yi, minus the predicted value, that's m times xi plus d. Now, the residual can be either positive or negative. In this case, for example, it's positive. In this case, it's negative. We want to take into account the residuals at all the data points. Well, we're going to have to set up a total error function. Perhaps one's first thought would be to sum the residuals, but I'm afraid this won't work. Just take a look at this simple example. These 3 points do actually lie on a straight line, and that surely must be the best fit. But if I draw any line through the central point, then the corresponding residuals will be equal and opposite. So in this case, the sum of the residuals will be 0. And the sum of the residuals then certainly wouldn't pick out the best fitting straight line. Well, you've met this kind of problem before. And one way round it is to take for the total error function the sum of the squares of the residuals. In other words, you take for each data point this quantity, and you square, and you sum the results. And what we're going to do is to use as our criterion for choosing the best fitting straight line this total error function, and we're going to find the line which makes that a minimum.
Before the program, we asked you to calculate that quantity for the particular set of data that we gave you for the elastic band. It was this horrible thing, and the last number was minus 1162200m. It involves two unknown quantities, m and d. And any pair of values for m and d will specify a particular line. And we've got to find the pair of values which makes this quantity the smallest. If we can do that, we'll have specified the particular line that we're looking for. Now, the problem is that we don't have a technique for investigating the minimum values of expressions that involve two unknown quantities. What we're going to do is to look at a clever method which will work in this particular case. Now, there are two stages in this method. The first stage will give us a relationship between m and d for the best fitting line. It won't be enough by itself to determine either m or d, but it will help us to solve the problem eventually. Now, to start off on this first stage, we shall first of all fix m. That's to say, try choosing the best fitting line from a set of parallel lines. First, let's set up a coordinate system with axes x and y. This line has a slope m, and the value of d is determined by the intercept with the y-axis. Right, now let's introduce our residuals, ei. Now, we've fixed m, and let's allow the intercept d to vary. As the d varies, not surprisingly, each residual also varies. Remember, we're going to be looking for ei squared rather than ei. So on the right-hand side of the screen, let's see how the total error function, sigma ei squared, varies as d varies. Remember, we are fixing m, so for each value of d, we get a corresponding value for the total error. We've calculated them on a computer for a particular numerical value of m. Now let's take some other values of d, still with the same value of m. And we can fill in the intermediate points. Actually, this is a parabola. Now, our intention was to minimize the total error. And for all these parallel lines, this one gave the smallest total error. Now let's do the same thing using a different numerical value for m. Again, we choose from these parallel lines the one which gives us the smallest total error. Let's try another set. Obviously, there's something important about this particular point, so let's look at it more closely.
We can see why all those lines pass through the same point by thinking about another of the problems you did before the program. You wrote the total error function as a quadratic in D, and this is what you got. Well, you then find the value of D, which made this a minimum, regarding m as fixed. And what did you get? Well, you found that D was equal to minus this coefficient, divided by twice the coefficient of d squared, 2 times 6. Well, this simplifies to give a relationship between d and m. In fact, it turns out to give you this relationship, 264 is 350m plus d. Well, what does this mean? It means that the line y equals mx plus d passes through the point 350, 264. Point 350, 264. But you'd already found that this number 350 is the mean of the x values, and 264 is the mean of the y values. This point is called the centroid. And what this algebra shows is that for any set of parallel lines, the one which minimizes the total error function must pass through this same point. Well, we don't yet know which is the best fitting straight line, but we do know that it must pass through the centroid. And that's where we start on the second stage of solving our problem.
Let's look at all the lines passing through the centroid and calculate the total error for each value of the slope. So on the right-hand side of the screen, we'll plot total error against m. This time, m is the variable on the right-hand side, and we can capitalize on the point x bar, y bar on the left-hand side. This time, we want to choose from this set of lines the one which gives the smallest total error. We get this one.
So that's given us a clear geometric picture of what's going on in this second stage of the problem. But how do I explicitly calculate the values of m and d that correspond to the best fitting straight line that we've generated? Well, here's the total error function again, and we know that this relationship holds between m and d. On the animation, we plotted the total error function against m. So algebraically, what I want to do is to use this equation to write the total error function in terms of m alone. That is, to substitute 264 minus 350m for d. Well, if I do that, I get, for the total error function, 175,000 m squared minus 53400m plus 4150, believe it or not. And this is now quadratic in m, and it takes its minimum value when m is equal to minus this coefficient, and that's 53400, divided by twice the first coefficient, 17500. And if I work that out, it turns out to be approximately 0.15. Now, to find the value of d, I just substitute this value of m in this expression here, and that gives me d. And it turns out that d is, again, approximately equal to 211. And when you think about it, thinking back to what Norman did earlier, the values of m and d that he got graphically were really quite good approximations to the ones that we've calculated here. And now we've found the slope and the y-intercept of the straight line, which is the best fit to the elastic band data, using this criterion of minimizing the sum of squares of the residuals. And the method that we've been using here, well, that's called the method of least squares.
Well, that solved the particular problem, but we can apply that same method to obtain a formula for fitting the best straight line to any set of data. So let's retrace our steps. First, we had a list of data, and this was it. But if we're going to argue generally, we can't talk about pairs of numbers. We'll have to use symbols. So we'll call the data pairs x1, y1, x2, y2, and so on. And if we've got n pairs, then the last one will be xn, yn. Then we've got to look at the total error function. And it's got this form. Here's the residual. You square it, add up the squares of the residuals, sigma ei squared. That's the total error function. And that's the expression that we want to minimize. Now, to do this, we go through two stages. First, we've got to keep m fixed. That's the slope of the line. And we look at a set of parallel lines. And we look for the line amongst this set which minimizes the total error. Algebraically, that means that the m here is fixed. And we regard it as a quadratic in D. So it would have this general form. The total error, AD squared plus BD plus C. The A, the B, and the C will involve the xi's, the yi's, and the fixed value of m. Now, the details are given in the text, but at the moment we just want to concentrate on this general form. Now, we know how to minimize expressions like this. You choose D to be minus B over 2A. And that gives us a relationship between M and D, because remember, A and B involve M. So that gives us a relationship between M and D, which turns out to be this, that y bar is mx bar plus D, where x bar is the mean of the x values, and y bar is the mean of the y values. So that tells us that the line must pass through the point x bar, y bar. That's the centroid. So out of any set of parallel lines, this is the one that's best. And that's the key to the next stage. We look at all the lines that pass through x bar, y bar, and choose the best one out of that set. Algebraically, that corresponds to finding the appropriate value of m, so that our expression for the total error, I have to get rid of D here. And I do that using this expression. That will give us the total error here as an expression in m. And again, it turns out to be a quadratic. So, remember what we're doing. We're using this relationship between m and D to eliminate D in the expression for the total error. That gives us a quadratic in m. And it turns out that the value for m, which makes this the smallest possible value, is given by this expression. It's rather a complicated looking expression, but you'll find all the details in the text. It's the mean of the product minus the product of the means, and it's all divided by the mean of the squares minus the square of the mean. Again, you'll find all these details in the text. Now, when you've got this value of m, you can use this formula to calculate the value of D.
Well, that's the formula. How are we going to use it to calculate m and D? Well, I think it's sensible to be systematic about a task like this, and I find that it helps to set out the work in a table like this. Here's the data, there's the x values and the corresponding y values. And what we're going to have to calculate are the mean of the x values and the mean of the y values, and then the products of the x's and the y's and their mean, and the square of all the x's and the mean of those numbers. Well, somewhere or other, Norman is here with the calculator. He's going to help me do this. Oh, so let's start off, and let's do the means first, shall we?
Okay.
Well, I think actually I can sum those numbers, since it's really just 1 to 6 almost,
Right.
isn't it? Quicker than you can do it in the calculator. I make it 2,100.
Yeah.
Actually,
I've accumulated those ones as well.
Um,
910000.
right.
Divide by
divide that
6.
by 6.
Okay. 151,666.67.
So now we've got all the pieces that go into our formula. The mean of the products of the x and y values, and the two means of the x and y values, which we have to multiply together. The mean of the squares of the x values, and then also we're going to need the square of the mean of the x's. So let's go on now and actually complete the calculation.
0.1525714.
Right, so that checks with the number that we had earlier. And of course, to find the value of d, we're going to use this formula once again. So that says that d is equal to the mean of the y's, that's 264, minus m, that's that number, times the mean of the x's, 350. Have you worked that out? I bet, you know, one of the disadvantages of doing this is you've probably had to key in that value
That's
of m
right,
again,
right,
haven't you?
put it in again. Okay, there we are. It's 210.6000301.
Right. Great. So that gives us the y-intercept for our best fitting line.
So that's the method of least squares. And we call it least squares because this particular straight line is the one which gives us the smallest value for the sum of the squares of the residuals. And notice the interesting way in which we got the formula. There's a very nice interplay between geometry and algebra. We used geometric arguments, which we then translated into algebra. And then finally, we set out a nice table so that we could do numerical calculations. And I hope, by the way, you can do them a little bit more efficiently than I did on the calculator. Still, having done that, you've got your actual straight line that you can draw with the given numerical values. And then you're right back to where we were at the beginning of the program. You can use it to make predictions. For example, according to this, if I hung a weight of about 320 grams on here, I'd get an extension like that, about 280 millimeters. But you've got to be careful about using this sort of thing to make predictions. Supposing I hung a weight of 1,200 grams on, the extension according to this would be about 425 millimeters. But think a moment. Do you really think if you hung something a bit over a kilogram on the elastic band, that's the sort of extension you'd get?